and start presenting. All right, let's see here. Okay, we are recording. That is good. Now let's go over here. What you should see now is my PowerPoint, and you should now see the actual regular presentation of the PowerPoint. So if someone cannot see that, please let me know. Otherwise, we'll go ahead and get started. So again, this is, again, I say again because the first time we didn't record, but this is chapter 2. We didn't get through the whole chapter, obviously, on Monday. We did get a few bullet points in, so that's what we're going to try to recreate right now. And like I said earlier, please let me know, pause me, stop me if you have questions. I love questions. But here we go, chapter 2. Every chapter in your textbook has this one little section that it starts off with. It's basically, why does this chapter matter? Why does it matter in the context of biology, and what does it matter in your life? So we'll talk about it really quickly. I'm not going to get into it too much. I'm going to just talk about these two. Hopefully you can tell from this picture that is bleached coral, and your book talks about how that happens. And one of the ways that happens is there's an increase in carbon dioxide in the atmosphere, and because of chemistry, that carbon dioxide dissolves into the water, and then it becomes something new. Then you get something, you get an acid, right? So that creates this carbonic acid, and that's what bleaches. That's what bleaches the coral. Another good one I like, and we're going to come back to this concept later, is this. I'm sure you can tell those are fries, and I'm sure because you're familiar with fries that what's happening is some salt is being poured on the fries, and that's what your book is focusing on right now, is the salt. Because salt is something called a compound, and you're going to learn what a compound is in this chapter. And the compound is made up of sodium and chloride. And sodium by itself is an explosive metal. It's very dangerous. And chloride by itself, or chlorine by itself, is a poisonous gas, right? So you have these two very dangerous things, and then you put them together, and it's something that we enjoy on our food, and it's been used in history to preserve food, right? So salt has been a very important part of our lives for a very long time. Your book also points out that you need salt. You need salt in your diet. But as I'm sure a lot of you are aware, too much salt is a bad thing. For example, it'll lead to high blood pressure is a great example. So that's another theme I'm going to come back to later, is how some things can be poisonous, or they can be bad for you if you have too much of them, but you do need some of them. So we'll come back to that concept throughout the chapter. Like I said, every chapter in your book starts with this, and sometimes I'll discuss it, sometimes I won't. Reason being is because it's not necessarily anything you need to know for the exam or to understand the chapter. It's just trying to get you interested in the chapter. So let's move forward. Another thing your book always starts off with in every chapter is a little, like a little story, a little something to look into that kind of ties that chapter to your everyday life. And every chapter, I usually ignore it because we're a little bit short on time. So I'm going to do the same thing for this chapter. But just so you know, whenever you see biology and society, feel free to read it. That's a good idea. Read it. So hopefully it'll bring this chapter to life for you, so to speak. But I'm never going to test you on anything in this portion of the chapter. So I'm just going to go through this. I'm not going to discuss it. As you yourself read it, if you want to, you can ask me questions, contact me and we can discuss it if you want. But again, nothing on there is going to be on the exam. On Wednesday, I did discuss it. But again, we're kind of short on time, so I'm not going to do that this time. All right, so let's jump into the actual meat and potatoes. This chapter is basically broken down to 2 sections. First, we're going to talk about some basic chemistry. Then we're going to discuss water and how that's important to life. And your book points out, and there's nothing to write down here, but your book points out that if you take any biological system, like anything we discuss in this whole semester, when you really get down to it and break it down to its core, really what we're looking at is chemistry. It's all about chemical reactions. And that's why we have to understand chemistry. And that's why this is such an important chapter. You might do okay in later chapters if you don't quite grasp chemistry, but you won't truly understand what you learn later if you don't truly understand chemistry. Of course, I shouldn't say it that way, because what we're doing is looking at the Cliff Notes version of chemistry. If any of you have ever had a chemistry class, you'll see this is going to be a lot different than that. This is going to be a lot easier. We won't be balancing equations or anything like that. So are there any questions so far? Okay. So the first thing I'm going to do is basically present you with some words that you need to know. First of all, you'll need to know them for the exam. And second of all, you'll need to know them so you understand what I'm talking about, because I'm going to use these words a lot and you're going to see them on the exam. So first word we're going to define is matter. And it's not from this meme, or excuse me, that's mass. Matter is anything that occupies space and has mass. So you need to know that for the exam. You just need to know that in general. That way, when you hear the word matter, you know what we're talking about. And if this was a non-scientific study, and if I weren't teaching you, and my son, my 8-year-old son, says, "What is matter?" To him, I would answer, "It's stuff," right? But for you, you should know that it's anything that occupies space and has mass. There's 3 states of matter. I'm sure you already know what they are: solid, liquid, and gas, right? So you think of water. I have water in my cup right here that I'm drinking. That's the liquid state. There's ice in it. That's the solid state. And if I were to put it on my stove and turn up the heat, it would start boiling and then evaporate, and it would be gas. So I'm sure you already knew that. But going back to this bullet point here, like I said, matter is anything that occupies space and has mass. So that brings us to the next question. What is mass? And mass, this is something you need to know, again, for the exam, and because I will use this word throughout the semester. Mass is just the measurement of the amount of material in an object. So again, if I were talking to my 8-year-old son, what is matter? Matter is stuff. What is mass? It's how much stuff. It's really that simple. Now where it gets a little bit less intuitive, I'm sure you all have heard of the word element. I'm sure you can think of some examples of elements, but you really need to know what an element is. That is something that can't be broken down into other substances by chemical reactions. And basically all matter, right, all stuff is composed of elements. So when we say it can't be broken down into other substances, let's use sugar as a great example. So sugar, as you'll learn later in the semester, so don't take notes, this is just an example. Sugar is made up of sucrose and glucose, right? Those are like 2 basic sugars themselves. So sugar itself can be broken down into those 2 things. And then from there, like let's talk about glucose, for example. That's made up of 6 carbons and 12 hydrogens and 6 oxygens, right? Those all can be broken down into those individual components. But then if you look at that 1 carbon, for example, or that 1 oxygen or that 1 hydrogen, that itself cannot be broken down, at least not by chemistry. No chemical reactions. So again, we're just talking about the basic building blocks of life. That's what an element is. So are there any questions so far? Okay. And also, like I said, you definitely don't need to memorize my example of what I was talking about sugar, but I would like to correct myself quickly. Sugar itself is called sucrose, and it's composed of glucose and fructose. But not that that matters for this exam, but I don't want to leave you with any misinformation. So if there's no questions about this slide, let's move on. Your book points out that there are 92 naturally occurring elements. You do not need to memorize that number. Your book also listed these as examples: carbon, oxygen, potassium, and gold. You definitely don't need to memorize that either. There are going to be some elements you need to know, and we'll talk about that when we get there. But these are just some examples. I assume your book chose these first 2 because carbon and oxygen are things we talk about a lot in this semester. They probably chose potassium, perhaps because you've already heard of it. You hear that a lot, especially when in conversations about the diet. And gold, that's another thing I'm sure you've heard of. So that's probably why your book chose it. Your book also points out that each element has a symbol that is derived from English, Latin, or German. And again, that's nothing you need to know either. But that also might explain perhaps why they use potassium as an example, because even though you would think potassium might start with a P, its symbol, but it's not. It's K. Gold is another good example because you might think it's a G, but it's not. It's AU. So again, just examples. This is just kind of easing you into the world of chemistry. There's nothing here that's going to be on the exam and nothing that you need to know that'll help you understand the rest of the chapter. So is there any questions regarding this slide? All right. This is an example of a periodic table. I'm sure you've seen it before. Like we said, there's 92 naturally occurring elements, and that's these right here. I'm sure if you look closely, you've seen before where you have the C, you have the element symbol, you have the atomic number, which is the number of protons, you have the atomic mass, which is the mass of the average atoms of that element. This is nothing to necessarily memorize, but it would help because the few times we do use the periodic table, for example, in lab, it would be nice to know what each of these means. So moving forward on these next few slides, we're gonna address these symbols and these numbers. So are there any questions so far? I think, oh, sorry, again, this is just an example. You do not need to memorize that the atomic mass of carbon is 12.01. It's just an example. They just zoomed in on that to show you an example of one of the elements. We are short on time, so I'm going to skip this. Usually I have a little guessing game because, in my opinion, basic chemistry is a little bit boring. I love more advanced chemistry, but basic chemistry is kind of boring, so I thought I'd throw something fun in. This is Mercury, and the hint was that thing's supposed to look like Freddie Mercury, and it also has the symbol for Mercury. That's copper, David Copperfield. That's lead. These are the symbols for the band Led Zeppelin, if any of you know who they are. This is iron, and the hint would be that thing looks like Iron Man. Anyway, done with the fun stuff. Let's get back to work. Now, here's some stuff you do need to know. So if you're taking notes, you might take notes on that. Like, this is an important slide for you. Your book points out that there are 25 elements that are essential to people. I might ask you to know that, but most likely not. What's important, I think, the most important, is you need to know that of these 25 elements, there are 4 of them that make up about 96% of your body weight. I call these the big 4. You don't necessarily need to know that they make up about 96% of the body weight. Just know that there's the big 4, and you need to know what they are. They are oxygen, carbon, hydrogen, and nitrogen. And by the time we get done with this chapter, which is obviously all about chemistry, and next chapter, which is about specific molecules that are important to life, you should know these, right? So you can study these if you want, but my guess is if you're actually doing the work in the lab and reading the book, you'll eventually just memorize these on accident, basically. But yes, these are the big 4. You need to know that they're the big 4. You don't need to memorize the specific 96%, but just do keep in your mind, like, that's a lot, right? So there's 25 elements. 96% of the weight comes from this. That means you got about 4% of the other ones that of the other 21 that make up your body weight. So are there any questions about this? We're going to discuss some of the other 4%, 7 elements specifically, and I'll talk about them. I'm about to give you some information, but this won't be on the exam, and it's not necessarily anything that you're going to need to know to understand things later in the semester. So that's why, in my opinion, it's a little bit less important. But we talk about calcium. I'm sure you've heard of it before. I'm sure you know why it's important to your body. For a couple of reasons. You have bones and teeth, and there's actually other things that do. Calcium does too, and you can look that up if you want for independent work. I'm sure you've heard of where you can find calcium. Usually people say dairy products, and that is correct, but you can also find it in sardines and green leafy vegetables, and probably some other sources too. And that's another thing that you can look up for independent work if you want. Next one your book talks about is phosphorus. I think fewer people hear about phosphorus than they do calcium. I think calcium is one of those more common ones, or commonly discussed, but phosphorus is a component of your DNA, and we'll talk about that later in the semester. And at that point in the semester, you will need to know a little bit about phosphorus, but for now, I'm just introducing it to you. Your book points out that phosphorus can be found in eggs, beans, and nuts. And again, I highly recommend looking this stuff up for independent work. Like, what else is phosphorus used for, and where else can you find it? I really think your book should have pointed out that phosphorus is a component of something called ATP. That's basically an energetic molecule. And in a sense, all of exam 2 is all about ATP. How do we make it? How does it get used? Things like that. But are there any questions about calcium or phosphorus? All right, we're making good time. So, excuse me, let me step back. Oh, that don't show the other 5. Oh, yeah, so your book doesn't discuss the other 5 of the 7, and so neither will I. But again, you can look them up for independent work if you want. It would be a great topic for, for independent work. The next thing we're going to talk about are the trace elements. And the reason they're called trace is because basically you need very little of them. These things make up less than 0.01% of your weight. So obviously they're required in very small amounts. And you might think, oh, well, because they're required in small amounts, they're not important. But that's not true. They actually are very important. And this brings up a subject that I meant to talk about earlier, but it reminded me. Another thing you can look up for independent work is the idea of what is a poison. Because there's a lot of things, like I mentioned with the salt, a lot of things can be bad for you if you have too much of them. But if you don't have enough of them, it can also be bad. So think of any element you want and look it up. Or for that matter, anything else you can think of. If you run across something in your everyday life, like certain medications, like how much is too much of Tylenol, things like that. But anyway, we will discuss some of the trace elements, the ones that your book discussed. We won't discuss all of them. Iodine is the first one your book discusses. If you don't have enough of it, you have something called goiter. And you can see this is a great picture, a great example of goiter. This lady has an enlarged thyroid because she did not have enough iodine. Where can you find iodine? You can find it in green vegetables, eggs, seafood, dairy products, and then iodized salt. So I'm sure you grew up hearing the word iodized salt, and I don't know if you ever thought about that and wondered what it meant, but that's what it means. Iodine has been added to salt. So that's one of the places you can get iodine. So any questions about iodine? And again, this is just an example. There will be no questions about iodine on the exam. Another great example that your book gives is fluorine. You might have heard it called fluoride. There's a chemical difference between those two words, but there's nothing you need to worry about for this exam, or excuse me, this course. Your book points out that fluorine, it's added to dental products, right, like toothpaste, things like that. It's also added to your drinking water, depending on where you live. Mostly in America, we do have it added to our drinking water. And it's important because it helps maintain healthy bones and teeth. And like this guy, for example, does not have very healthy teeth. Doesn't seem to bother him, but it is what it is. And this is also one of my favorites, and I'm glad your book included it because I have a lot of conspiracy theorist friends, and they constantly will share fake information or misleading information on social media. And this one I see a lot. You see a lot of things about fluoride and fluoride because sure enough, if you have too much of it, it is bad for you, right? Just like everything else we've listed so far. But if you have too much of it, it's bad for you. But if you don't have enough of it, that's also bad for you. So again, I highly recommend looking that up if you want for independent work. How much is too much? How much is not enough? So any questions about fluorine? Okay. Going back to this idea of elements, iron is another great example. I don't remember if your book included it or not, but if you see things like cereal, for example, or formula, stuff like that, you might see that says it's fortified with iron. And what that means is they do literally put iron, the metal, they put that in your food. And if you click this little link right here, it's been a while since I've looked at it, so I don't remember which version of the video it is. But there's a video of somebody who took some cereal and they put it in a blender with some water, so it was a nice homogeneous mix. And then they put a magnet next to the blender, right? And all the iron obviously was attracted to the magnet. So you could see the iron in the cereal. And I've also, and again, I don't remember which version of the video it is, there's at least two versions that I've seen. There's one of them that's kind of like a science experiment. This guy's just demonstrating and said, oh, if you look at this is the iron in the cereal. And another version I've seen is one of those scare tactic type videos. Again, something misleading where someone's saying, you should see what Kellogg is putting in the cereal. Let me demonstrate. And they show, and it's trying to make you scared of the fact that there's iron. But anyway, the point is you need iron. It is fortified. Some things are fortified because they literally put metal. They put the iron in there because you need it. So anyway, are there any questions about this? Okay, moving forward. This is a great infographic. You do not need to memorize any of it, but I really like it. So you can see here, these are the big four: oxygen, carbon, hydrogen, nitrogen. Yes, your book tells you specifically how much there is. Obviously, there's mostly oxygen, less carbon, less hydrogen, less nitrogen. But for the purposes of this course, this 100 level course, I don't think you need to know that. Just know the big four. Same thing with this. You definitely do not need to memorize this entire list. Same thing with this. You definitely do not need to memorize the entire list of the trace elements. But again, if this is interesting to you, I highly recommend looking this stuff up for independent work. Are there any questions about this figure? Excuse me. All right, we'll move forward. Here's another word that you need to know. You need to know what a compound is in the chemistry sense. And that is when elements combine, right? Two or more elements will combine in a fixed ratio, and that is what's called a compound. So your book gives two common examples: table salt, which we've already talked about, which again I love because, you know, sodium, very dangerous, chlorine, very dangerous. Put them together, and it's something that you actually need in your diet. And then, of course, water. You're all familiar with water, H2O. And that's, again, what we mean by fixed ratio. Water is always H2O, two hydrogens, one oxygen. If it's something different than that, then it's technically not water. Same thing with table salt. It's always going to be one sodium, one chloride, because if it's anything different than that, technically it's not table salt. So are there any questions about what a compound is? Okay. Which brings us to some more words you need to understand. And now we're getting past just vocabulary. I'm going to give you some vocabulary words about atoms, but now you kind of need to understand how things are built. And that's what we're going to talk about with atoms. Your book points out that each element, so all those 92 naturally occurring elements and the big four and the trace elements, all those things we've talked about, each element consists of one kind of atom. And an atom is the smallest unit of matter that still retains the properties of an element. So for example, and you do not need to memorize this, this is a depiction of a helium atom. And anything less than this, like if you were to take away one of these protons, it would just no longer be helium. It would be a different element. So this is the smallest unit, right? And that is something you should know for the exam. You need to know what an atom is. Are there any questions regarding what an atom is? At least the definition of an atom. All right, so let's talk about the structure of an atom. Now that you know basically what an atom is, you need to know what they're made of. They're made up of three parts: a proton, an electron, and a neutron. And you need to understand that for the exam. And you need to know, just to know how chemistry works, basically, you need to know that protons are positive. You need to know that electrons are negative, and you need to know that neutrons are neutral. And hopefully that should be easy for you to remember. Obviously, neutron is going to be neutral. It's in the name. Proton and positive, those both start with P. So therefore, by process of elimination, you have neutral, you have positive. The only thing left is negative, and that's the electron. And the way you could remember that is, generally speaking, getting electrocuted is a negative thing, right? So think about it that way. But yeah, that's what atoms are made of. That's as deep as we get in this class. If you want to look deeper into it for independent work, you could ask yourselves, well, I don't know, what's a proton made of? What's a neutron made of? You can look into that if you want, but to keep this simple for this 100 level course, you need to know that this is what an atom is made of, these three things. Another important thing to know, and you'll get really familiar with this in the lab, I hope, is that the number of protons equals the number of electrons. Unless someone says that this is a charged atom, right, in which they'll let you know if it is, or I will let you know if it is, but unless otherwise stated, the number of protons equals the number of electrons. And when that happens, that means the net electrical charge is 0, and therefore the atom is neutral. Are there any questions so far? All right. So again, we're talking about the structure of an atom. We have already listed the 3 parts, right? So when you put 2 of those parts together, the protons and the neutrons, those are all in this center, right? In the central core of the atom, and that is something we call the nucleus. And that's not to be confused with the nucleus that we discuss when we talk about cells. It's only in chemistry. That's where you find the protons and neutrons. And for the exam, you do need to know that the nucleus, right there in the middle, that contains protons and neutrons. And I might also ask you where the electrons are. And the electrons move around the nucleus. And I'll go into that in the next few slides. We'll talk about how they move around the nucleus. But before I do, hopefully you remember at the beginning of the chapter, the stuff I kind of moved past quickly because I told you it won't be on the exam. We talked about radioactivity. And your book doesn't really get into this, but I thought I might bring it to your attention really quickly. It kind of simplify radioactivity for you. It gets harder if you really look into it, but this is a good simple explanation. We see here, this is uranium, for example. There's a lot of protons, right? If you were to look it up on the new periodic table of elements, you would see that uranium, its number is 92. It has 92 protons. Now, has anybody ever tried to put like a plus side of a magnet to another plus side of a magnet? Well, you don't have to answer that, but I'm sure you have. I'm sure you know that they repel each other, right? And the same thing happens with protons. Here we have 92 protons, positive things, that are repelling each other, but there's this force that keeps them together. It's a lot of force. It's a lot of energy that keeps them together. And again, you can go deeper on your own if you want and look into that for independent work. What is the force that keeps it together, right? Look it up if you want. But that's what radioactivity is once these things start busting out, right? Because there's a lot of energy keeping them together. Once they start busting away and releasing energy, that's basically what radioactivity is. But again, you can look into that deeper if you want, but for the exam, you just need to know what the nucleus is and the fact that electrons move around the nucleus. So are there any questions so far? All right. Here's basically a picture of everything I've said. Here's the nucleus. Again, you've got your protons and your neutrons right there in the nucleus. And then floating around on the outside, you have electrons. So are there any questions so far? All right. Another thing that's very important that's for you to remember, because it'll be on the lab and on the exam, is that the atoms of a particular element have the same unique number of protons. So all carbons, for example, have 6 protons. All helium have 2 protons. All hydrogens have 1 proton. And that number of protons, is what's known as the atomic number. So you need to know that for the exam, and you need to know that to understand some of the stuff we're going to talk about later. You need to know that the atomic number is the number of protons. And another thing you could write down if you take notes is, if you're going to shorthand it, protons, if you change the number of protons, you change the element. Okay? So an element, as far as we're concerned, it's defined by its number of protons. So again, helium, right? It has 2 protons. That's what makes it a helium. If you take one away and you only have 1 proton, at that point, you then have hydrogen. So that's what the atomic number is. Are there any questions about the atomic number? All right, that brings us to something called the mass number. And the mass number is the sum of the protons and the neutrons. So in a way, it's like saying, how much does it weigh? So if we have, for helium, we have 2 protons, we have 2 neutrons, therefore the mass number is 4. Of course, if you look at this, there's nothing on here that tells you that there's 2 neutrons, but I do know that the atomic number is 6 and that the mass number is 4, and that's a difference of 2, right? That tells me that there's 2 neutrons. And there might be a question like that on the exam. There's definitely one like that on the study guide. You can always figure out how many neutrons something has by using that basic math, right? because you know how many protons it has by its atomic number. If I give you the mass number, then you can just figure out the difference, right? So 4 minus 2 is 2. Are there any questions about that? All right. So you see here, we've already talked about mass number and atomic number, which is here and here, right? One of the things we haven't talked about yet is this right here, which is the atomic mass. And that's where it gets a little bit confusing, because we talked about the mass number, but then we talk about atomic mass, and that's slightly different. Let's talk about it now. It's close to the mass number, but it may differ. It represents an average of all naturally occurring forms. And this is a great example. Hydrogen, almost all hydrogen in the world has 1 proton, 0 neutrons, and 1 electron. And because of that, let me see if I can see there. Now you can't see it, but if you have access to a periodic table, you can look at it. And if you were to look at it, it would tell you that the atomic mass of proton, excuse me, let me back up a little bit. If you were to look up the atomic mass of a proton, it is 1.008, right? And it's not because there's any hydrogens that weigh 1.008. It's just that if you take an average, right, of all the different types of hydrogen in the world, that's what you come up with. And I think a good example for that. Yeah, let's talk about it. Yeah, I'll get back to it. Okay. So think about this. If I were to ask you a question, how many fingers does the average human have? And that includes thumbs too. I'm not trying to trick you. Can anyone who hasn't had this lecture already tell me how many fingers the average human has? What's the average finger number for humans? No one wants to guess? It's okay if you're wrong. I'm actually hoping somebody is kind of wrong.
I mean, I've had the lecture, so I don't really want to answer. I don't know if anybody else.
That's okay. I'll just move forward. So usually people would guess that the average human has 10 fingers, right? Because when you think about it, most humans you see, they have 10 fingers. But if you were to actually figure it out, I'm sure it's probably like 10 point something something, or maybe 9 point something something, something very close to 10, but not quite 10, because there's a lot of humans that are missing fingers, right? And there's a lot of humans that have extra fingers. So it isn't that your average human is like, if you look at a human, like you go out and look at everyone's hands, it's not like most people you see are going to have 9.8 fingers, right? What it means is most humans have 10 fingers. Some people have fewer, some people have extra. And just like that weird statistic, I don't know if you've heard it before. I don't even know if it's true, but someone says like the average family size in America is 2.4 children, right? No one has 0.4 children, right? That's not a thing. What they're saying is if you were to take the average, that's what it is. But are there any questions so far about atomic mass? We're about to talk about it a little bit more. All right. So that brings us to something called isotopes. And before we jump into this, I want to remind you of something I said earlier. If you change the number of protons in an element, then you change the element. And I used helium as an example. Helium has 2 protons. If you get rid of one, you have hydrogen. If you add one, you have lithium, right? So if you change the number of protons, you change the element. But that brings us to something called isotopes. And an isotope is an alternate mass form of an element. And that's the definition, but that's probably not how the question is going to be on the exam. I'll come back to that. Isotopes have the same number of protons, obviously, right? Because if you change the number of protons, you just completely have a different element. They have the same number of electrons, and we'll talk about what happens if you change that later. They even behave identically in chemical reactions, but, and this is the important part if you take notes, isotopes have different numbers of neutrons. So again, if you change the number of protons, you change the element. If you change the number of neutrons, then you have yourself an isotope. And this is an example. It's not from your book. This is carbon. There's different forms of carbon. There's carbon-12, right? They call it that because its mass number is 12, which means it has 6 protons and 6 neutrons. 6 and 6 is 12. Then there's carbon-13, which is 6 protons and 6 protons and 7 neutrons. And then carbon-14, 6 protons and 8 neutrons. So you can see here, you can change the number of neutrons and still it's the same element. It is just then called an isotope. And again, going back, that's where we get this idea of the atomic mass, right? So if you were to look up carbon on the periodic table, it doesn't say that its atomic number is 6, even though most of the carbon in the world is carbon-12. If you look at it, it's a decimal, right? It's 6 point something something, right? Because there's the existence of these different neutrons in nature. Does anybody have questions about what an isotope is? All right. This is something I've already talked about. Again, this is probably a fake picture, but the point here is not all humans have 10 fingers, right? So because of that, the average, the average human hand is not going to be 10, right? It's going to be 10 point something, 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 or 9 point something, 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 something very close to 10. And again, going back to carbon's atomic mass is 12.011, right? That's really close to that's really close to 12. And what that tells you is that most carbon in nature is this. There's a lot of carbon-12 out in the world. There's even fewer carbon-13s and carbon-14s. Because think about it, if there was more 13s and 14s, then this number would be a lot higher. And that's all that means. And again, this is an example. There will be no specific questions about the differences between carbon-12 and 13 and 14. This is just a great example of what an isotope is, and also how that relates to the atomic mass. So are there any questions on isotopes? All right. Your book talks about radioactive isotopes. And in my opinion, that's not very important in the grand scheme of this semester. So I'm going to brush through it pretty quickly. A radioactive isotope is simply an isotope that's radioactive. And what do we mean by radioactive? That means the nucleus, so the protons and the neutrons, right? That just means it's decaying spontaneously. And I was briefly discussed that when I gave you that example of the uranium and how there was 92 protons squeezed into that nucleus. And there's a lot of energy keeping it together because they don't want to be together. That's all this is, right? So as things are decaying, right, you're losing protons and neutrons and energy. It's just leaving the elements, leaving the atom. And that's what radiation is. And as we brushed past at the beginning of the chapter, radiation can damage cellular molecules because it's high energy, right? It can hurt things. And because of that, it also poses serious health risks. You don't need to know that for the exam. Again, it's not very important in the grand scheme of this chapter. Same with this. Your book does point out some natural sources of radiation. Radon is one of those. I don't know if you ever purchased a home. You've probably heard that word because homes have to be tested for radon. It's a radioactive gas and it causes cancer. Anyway, are there any questions about what a radioactive isotope is? All right, moving forward. Every chapter in your book has this thing called the process of science, where they explain an experiment, like a real experiment someone did, and it's in the context of that chapter. So in this case, it's how effective is radiation in treating prostate cancer? But as is always the case with all the chapters, I'm always going to skip the process of science because we're a little bit short on time. It's nothing that you need to know for the exam. I do recommend reading it because it really gets your mind thinking in a scientific way, right? You get familiar with the scientific process. It'll help, but you definitely don't need to read it. We're always going to skip it. I will always answer questions if you have any questions about it, but let's go ahead and skip on through it. You will get no questions about this on the exam. And that is where we ended on Monday. So that is where we will end today. Does anybody have any questions on anything we've covered so far? Or for that matter, any questions about the semester in general? You have questions about independent work or attendance or anything like that? Because we are recording, so questions are good. I can get the answers recorded and we can share it with your classmates. All right. If there are no questions, I'll remind you, you should email me to let me know that you attended, so to speak, attended this lecture so I can give you some extra credit points or some independent work points, as it were. And as far as I'm concerned, we are done. So if you guys don't have anything, I'm just going to X out of here and see you on Wednesday, hopefully.